All right, watch and listen carefully here, guys. Okay, so both of these are just like the v equals d over t, but multi-part trips that we've been doing already. Okay, so we have in the first part, the bus travels 2,500 meters north in 75 seconds, and then turns around and travels 18 meters per second south for 55 seconds. Okay, we are looking for the total distance traveled and the average velocity of the bus. Give them a mark for their givens. The part 1 displacement, 2,500 meters north in time 75 seconds, 18 meters per second south in 55 seconds. Those are their givens. Okay. Now, if I want the total distance traveled, I need to know how far it goes in both parts. Okay, that's kind of the first thing I got to calculate. Don't have to do anything with part 1. They already told me how far I went there, but they did not tell me how far I went in part 2. All right, so I'm going to calculate displacement, because as long as I'm dealing with only one part of the trip, displacement and distance have the same magnitude. Okay. All right, so displacement is velocity times time, which is 18 meters per second times 55 seconds for 990 meters south. All right, so if they have that, okay, this part here, okay, whether they got the 990 or not, you can give them a mark for their method there. Okay, as long as they have d equals v times t, or they have 18 times 55. All right, next mark is for adding those two together, not taking into account that one is north and one is south, because distance is scalar. Okay, so that is this step right here. They get the mark not for the operation this time, but for the answer, 3,490 meters. If there's a direction on that, it's wrong. Okay, and there must be units, and they must be meters. Okay, if the units aren't meters, it's also wrong. If it's missing units, it's wrong. Okay, we've got to have all of that. So far. Okay, we haven't done the second part. Now, average velocity of the bus. I need total displacement and total time in order to calculate velocity. Displacement cares about distance, so does velocity, or sorry, direction, sorry, so does velocity. So I take my two displacements, 2,500 north, I add 990 south, or subtract 990, okay, and then divide by the total time. So if they have something like that, give them a mark, so either these or this, okay, one or the other for the numbers being plugged in. Okay, they have to have done that right with the addition, with the subtraction or adding a negative on there. And that will give us, for our fifth and final mark, 11 point, actually, is that the right number of significant figures? It is not. So we should have 1,510 divided by 130. Yeah, okay, so it should be 12, not 11.6. Okay, 12, oh, still have the one on there. 12 meters per second, okay? And actually up here, for the total distance, that should be 3.5 times 10 to the 2. I'll let that one go, okay? Sorry, no, it shouldn't. No, that one's decimal places. That one's right the way it is, sorry, because it's addition. But this has to be 12 meters per second north. If it isn't, it's wrong, okay? It's got to have the right number of significant digits, the right direction north, and the right units, meters per second. Okay? Questions on that one? All right, so that one's out of 5. Okay, for question number 2, okay, running a line drill, a basketball player runs forward 15 meters at 10 meters per second, then runs backward 10 meters for 1.1 seconds, then runs forward another 15 meters in 1.6 seconds. How many significant digits is our answer going to have here? 2. Everything has 2 in this one, so our final answer is going to have 2. All right, we're looking for the average speed of the basketball player. Does direction matter at all in this question? Not at all. Okay. So for the first part here, they run at 10 meters. So give them a mark for their givens. Okay. So if they have kind of that stuff we were given at the beginning written out, okay, they're good. If I want total distance and total time, which are the two things I need, right? I was not given the distance for every one of them, but not the time for all of them. Okay. So I have to find the time for part 1. So if they have t equals d over v, okay. So they showed the manipulation. Give them a mark for that. And if they have 1.5 seconds, give them a mark for that. Okay, no, that's 3 now. Okay, 1 here for givens, 1 here, 1 here. That's 3 marks. Okay. Our next mark is for starting the whole total displacement over total time, or sorry, total distance over total time operation. So if they have something like this, okay, either one of these, so 15 plus 10 plus 15 over all the times added together, or they just have 40 over 4.2, that's fine as well. Okay. For their 4th mark and their 5th mark, 9.5, 2 significant figures, meters per second. 5. Okay. Questions on number 2? Emily? Nope, it's got to have the right number of significant figures, 9.5. Okay. Give him a mark out of 10, let him see it, and put it on the desk right here in front of Shaz. Okay, we talked about building graphs. We started doing that. We did the one of diameter versus circumference yesterday, okay, and we found that the slope should have been equal to pi, okay, and most of us were, between 3 and 3.3 for our slopes, which is pretty good, okay. So we're going to go over that a few more times today. Today we're going to look a little bit more at y equals mx plus b, okay. We kind of used it a little bit yesterday, but on this graph it's going to be even more important, okay. So we'll be looking at that and a couple of other graphs and looking into a little bit of interpreting graphs and things like that. Tomorrow, we'll have the Chromebooks, and I'm going to show you how to use Google Sheets to do your graphing, and then you'll never have to do another graph on paper again. Yeah, I know it's awesome. Doing graphs on paper sucks. Okay, and then on Monday we'll do our lab where we run our carts down the hallway and measure in time, and then we'll do graphs with real data. Okay, and that'll be a lab that you'll hand in. Okay, and then from there we'll probably move on to some more stuff about interpreting and reading, the 2 kinds of graphs that are going to be important for us in this unit, and then we'll move on to acceleration after that. So that's probably the next couple of weeks, okay, right there, that we'll be doing that. Okay, so what I want you guys to do right now is build a graph of this data, remembering a couple of things. Okay, your graph needs a title, your axes both need labels with units. To pick your scale, you take the largest number that needs to fit on that axis and divide it by the number of boxes that you have to fit it in. That tells you what each box should be worth. If it's not a convenient number, which way do you round? Up. Always move to a convenient number that is bigger than what you have, but make sure it's bigger and close. Okay? Don't round 26 to 50. Okay? That's not going to work out very well. All right? So remember those things, plot your points, and draw yourself a best fit line. All right, I'm going to give you a few minutes to get ahead of me, and then I'll do it on the board as well, and we can compare our graphs. Now, this experiment here, okay, is saying they want to plot a graph of length versus force for the following experiment done on an elastic band. So here's what they did. Okay, they picked a bunch of forces and measured the length of the rubber band at all of those forces. Okay, so which thing should go on the x-axis? Forces. Okay. Force should go on the x-axis because it's the manipulated variable. Length of the elastic band should go on the y. Okay? All right, I'll give you a few minutes to get ahead of me there. Okay, your scale might be different. Remember, your graph paper's got a different number of boxes than mine. Okay, so it's okay if your scale doesn't match what mine is. I've got an odd number, weird numbers of lines on mine. Okay, so what I found for the force scale, I had to fit 11 on the bottom, and I had 30 spots. Okay, so when I divided that out, it looked like it would fit if I made each line worth 0.4. Okay, because I think it came out to 0.36 per line, and I didn't want to use that. 0.4 seemed a pretty easy one to use, so I just marked every third line as 1.2. Okay, it was easy to count by. And then for the length, I had to fit 28.5 on 35 lines. You know what? That's pretty close to 1. It came out to 0.81 something, and I was like, you know what, that's close enough. I'm just going to round it to 1 because that's really easy to count by. So I made every line worth 1. Okay, so now I've got my scale on there. My axes are all labeled, force on the x, length on the y. I've got a title, elastic band graph, length versus force. Now I've got to plot my points on the graph. Okay, so my first point is 0 and 6.5. So here's 6, so 6.5 would be right there. All right, and then my second point is 1 and 8.5. So 1 would be right smack in the middle of this, and 8.5 would be right about there. Okay, then 3 and 12.5. Okay, so 3 will be right in here somewhere, and 12.5 will be right about there. Okay, so am I eyeballing a lot of these points? Yeah, okay, and which is why we don't use them when we're doing a slope calculation, right? Even if they end up on the line, I can't be sure I put them in exactly the right place. Okay, 16.5 and 5. Okay, so 5 would be right about here, and 16.5 right there. Okay, 7 and 20.5, so 7 will be right here. 20.5 will be right about there. 24.5 and 9. Something like that. And 28.5 and 11. So 11 will be right about there. All right, so there's my points all plotted on my graph. What's my next step? Draw my best fit line. Okay, so for you guys, that means using a straight edge. For me, it means using the straight line tool. Okay, should I start at the origin for these points? No, I shouldn't, because that's not going to help me follow the general trend of my points. My points don't start at the origin. Okay, it's quite clear that they don't do that. So I want to draw a line, regardless of where I have to start it, that follows the trend of my points. Okay, so I'm going to go something like this, and then I might adjust it in a minute. Okay, but not by very much. I think I'm going to keep it right there, actually. All right, that follows the general trend of my points. Doesn't go through 0, 0, and that's okay. Okay. All right, so now what do I have to do with that line? I should probably find its slope. Yeah, I should probably find its slope. Okay, and I want to do that using y equals mx plus b. Okay, can I find b on this graph? Okay, well, b is the y-intercept. That is, where does my line cross the y-axis? And it looks like it does it right here at 6.5. Okay, because I kind of started there on purpose. Okay, so right there at 6.5, that's what I'm going to say b is. So b will be 6.5. Okay, and then I need a grid intersection that I can use to get y and x from. That way I can solve for m. All right, I've got a nice grid intersection right here. It's almost perfectly through the intersection, not too high, not too low. All right, so for that one, I'm going to go across to here, and its y value is going to be 22, and its x value is going to be 7.6. Okay, so now I'm going to manipulate for m. So to do that, what do I move first? Subtract the b, right? Move what's not attached first. So y minus b, I just calculated the rise of the graph. The difference between b here and y here is how much the line went up, the rise of the line. Okay, and I'm going to divide that by x. Well, since x is 0 here at my y-intercept, okay, this x value, 7.6, is also the run of my line. Everybody follow there? Okay, so I'm going to have 22 minus 6.5, okay, so y minus b divided by 7.6. Oh, come on, turn on. Sorry, not 22.5, 22 minus 6.5. Okay, so my rise is 15.5. I'm going to divide that by my run, 7.6. Okay. So the slope of my line is 2.04, we'll say. What are my units for that? Centimeters. What are my units on the x-axis? Newtons. That's the units for force. Newtons. That's what N stands for. Okay. So the units here are centimeters per Newton, which would kind of make sense. It's how many centimeters longer it gets every Newton of force that is applied to it. Okay? It gets 2 centimeters longer for every Newton of force that we apply. Okay? That's what the slope is telling me, centimeters per Newton. Okay? Everybody all right with that? Okay. The y-intercept, b. What is that telling me about the rubber band? Remember that this is an experiment where I'm applying different forces to the rubber band and measuring how long it is. Right, it's telling me the unstretched length of the rubber band. Okay, the y-intercept is telling me how long is the rubber band when there's no force acting on it. It's 6.5 centimeters long. Okay, sometimes we like to know that as kind of a starting point for an experiment, right? What happened to your responding variable before you did anything? Okay, that's essentially what the y-intercept is telling you. Okay, you haven't manipulated anything yet because x is 0. So where did you start from? That's what the y-intercept is kind of all about. Okay, all right. How many people are getting or have already calculated their slope? Okay, I'm going to give you a few more minutes. Just compare to that one. See how close you get. All right. Now I want to go over with you guys why we want to use y equals mx plus b as opposed to rise over run. Okay? And it's because rise over run will only get you the slope. I think I told you that yesterday. It won't do anything else. Okay? Y equals mx plus b allows us to do something called extrapolation. Okay? And what extrapolation is using data you have to calculate / predict data that you don't have. All right? So in other words, for this rubber band graph that I've got here, okay, this graph, now that I have m, could allow me to calculate several things, like how long will the elastic be if I used a force of 15 newtons? That's not on my graph. I can't use my graph to find that number, okay? But I can use the slope of my graph to calculate what it might be, okay? As long as everything stayed linear, which for a rubber band, actually at a certain point it doesn't, but we'll say it does for this rubber band, okay? Or I could calculate the force required to stretch the rubber band to 20. Okay? I can calculate any of those things now using the slope that I just calculated. Okay? So here's what we're going to do. We are going to extrapolate, okay, for 2 different things. Okay? So for number 1, the first thing we're going to extrapolate for, so write this down somewhere, maybe on the back of your graph or something. All right, so we want to calculate how long the rubber band will be when stretched with 15 newtons of force, a value that is beyond the end of our graph. Okay, so they're asking me to find length. Is that on the y-axis or x-axis of my graph? It's on the y-axis. All right, so I'm solving then for y. I'm going to use this equation, y equals mx plus b. All right, I know what m is because I already calculated it. It's whatever your slope is. Okay, mine was 2.04. All right, and I know what b is. It was 6.5. Those numbers stay. Okay, m and b, once you've got them calculated, are valid for anything, for any value of y or x. Okay, what else did they tell me? They told me 15 newtons of force, which is x. So I know m, x, and b. I can calculate y. I'm extrapolating for a value of y that is beyond the end of my graph. All I have to do is plug in the numbers and solve. Okay, so for this one then, that's going to be, for me, 2.04. For you, whatever your slope came out to. Okay, times x, which was 15 newtons. Okay, and adding 6.5 to that, right? I have to add how long the rubber band was at the beginning. That's essentially what I'm doing here. Here's how far I'm going to stretch it, plus how long it was to start with. That's essentially what I'm doing. Does everyone follow that? Okay. So when I do that calculation, 2.04 times 15 plus 6.5. All right, so it's going to be 37.1 centimeters long. This must be a very stretchy rubber band, right? Because that's what now? We're getting to be that's 6 times longer than it was, close to 6 times longer than it was at the beginning. I don't know too many rubber bands that stretch like that. Okay, all right, so 37.1 centimeters. Does that have the right number of significant figures according to what I was given? 2. Okay, so 37 centimeters. Okay, so that's one of the extrapolations that you can do. You can extrapolate for a y value. You could also be asked to extrapolate for an x value, so that would look something like this. Okay, they would ask us how much force is required for a specific length. In this case, 45 centimeters. Did you stay on the line? I was watching those. Oh, okay. Okay, so we've got to extrapolate now for an x value. So I still start out with y equals mx plus b. I still know b and m, and now I know y. They gave me a length in centimeters. I'm solving for x. What should I move first? B. All right, so I'm going to go y minus b, and then I'm going to divide by what? I'm solving for x. M. Okay, now I just plug in my numbers. So I'll have 45, the y value they gave me, minus 6.5, divided by 2.04. All right, so I'm going to require 19 newtons worth of force, 2 significant figures. 6.5 only has 2, the 45 only had 2. Okay, so I'm going to be looking at 19 newtons worth of force. Okay, that's what you'd be asked to do with a graphing question in Science 10. Calculate the slope for me, and then calculate a couple of values that aren't on the graph using y equals mx plus b. Okay, that's as far as you're going to be asked to do. And really, realistically, that's all you're ever really going to be asked to do using graphs, with the exception of maybe a couple of little things with specific types of graphs. Question? Okay. All right. All right. We got more graph paper there? Grab another sheet. I was pretty sure I made enough for everyone to have 3. Okay, grab another sheet of graph paper. I want you to try this one. For this graph, what we're doing is we're trying to find out how thick a book gets based on how many sheets it has. Okay, so which thing should go on the x-axis? Number of sheets. Okay, the number of sheets influences the thickness of the book. Okay, so we're going to put number of sheets on the x-axis, we're going to put thickness of the book on the y-axis, okay, and plot our graph. Right, so I'll give you a few minutes to get ahead of me there, and then we'll look at it together. Okay, let's have a look at this graph here, guys, real quick before the bell goes. All right, so when you plot your points, okay, it becomes quite obvious that you are not going to be starting at the origin when you draw the best fit line for this graph, because it doesn't go anywhere near there according to the trend we see. Okay, so when I draw my best fit line, that'll work. That's not great, but it'll work. Okay, so here's what I've got. I've got B equaling 6, maybe slightly more than that, but I'm going to say it equals 6, okay, millimeters. And I've got to calculate, okay, my slope. So y minus b over x is going to give me the slope. Paying attention, please. All right, I need to find a good grid intersection somewhere on the graph. This one here looks pretty solid. Okay, so I'm going to go across there. Y is going to be 14.2. And x is going to be 56. Okay, so m for my graph is going to be 14.2 minus 6 over 56. All right, so I'm getting a very small number, and that's okay, right? I'm going to say it's 0.15 here because I've got about 2 significant figures. So 0.15. My units are millimeters per what? Sheet. The slope of this graph tells me the thickness of each page of this book. Okay? Millimeters per sheet. All right? So, what could I do with this graph? Listening, please. I can predict the thickness of a book given the number of sheets, or I can calculate the number of sheets given the thickness of the book. There you go. Okay? I can solve for y or I can solve for x, just like we did on the last one with the rubber band and force. All right? Okay. Tomorrow, I'm going to show you how to do it the new way, the better way, okay? The way that saves you all this time and agony. Yeah. Well, using y equals mx plus b is still going to be the same. Manipulating and doing all that, that's the most important part. Mallory.
We got like different numbers.
That's okay.
But we still got the same number, so like, is it going to be like that with every graph that we do?
Yeah, because you drew your best fit line slightly different than mine. So it's okay that you get a slightly different number than me. Yeah, because your intercept was 5 and mine was 6. So your line was probably a little steeper than mine?
But we still got 0.1.
Yep, that's okay.
Doesn't the, like, the technology one give you, like...
It does. It'll